Okay. Can you see the presentation?
Yes.
Okay. So,
Please start.
okay. Hello, everybody. Thank you for coming today to my project Defense. My project name is Effect of 3D Shear Wave Variability on the occurrence of liquefaction, the Maule earthquake case. This project is within the framework of a bigger research project and named Evaluation of Liquefaction Potentially in Subduction Zones, a project I am part of. So, the table of contents. First, I want to activate the laser. The table of contents, what are we going to present in this presentation? Firstly, I want to introduce the topic. Then I will expose my hypothesis and goals, the methodology and how we want to achieve these goals, our schedule, and lastly, what are some preliminary results we already have and the bibliography. So for starting with the introduction, I want to answer some questions to introduce the topic. The first question is, when an earthquake-induced liquefaction occurs? Firstly, we need to know that liquefaction is a phenomenon wherein a saturated sand subjected to cyclic shear loads loses a large percentage of its shear resistance and flows in a manner resembling a liquid. Therefore, soil liquefaction will occur when the strength of the soil subjected to the seismic load decreases because the pore water pressure increases because of the seismic excitement. The second question I want to answer is liquefaction in megatrust environments different from shallower and or smaller earthquakes? We need to know that liquefaction can occur both in megatrust earthquakes as well as in crustal earthquakes. The difference will be that megatrust earthquakes tend to be deeper, tend to be stronger. The magnitude of the megatrust earthquakes is big, and they have different focal mechanisms than in shallow earthquakes. Therefore, the frequency content, the duration, and the intensity measurements will be most likely be very different. An important thing to remark is that most of the liquefaction studies and relationships are derived from sites in crustal environments, and also there is a lot of events in subduction environments that have like thrust focal mechanisms. But megatrust earthquakes, like which can happen in, for example, in Chile, in Japan, there are not so many case histories, and this is something we should not overlook. And the last question I want to answer is, what are the effects of liquefaction? First, I want to talk about ground motion alteration. Here we see a time series, an acceleration time series of the Niigata earthquake in Japan in 1964. We see that before the 6 seconds, the acceleration time series is what we expect from an earthquake. But after that, the frequency content of the time series changes abruptly. It seems to happen that the high frequency components of the motion don't seem to reach the surface, and this is linked to the decrease in soil stiffness because of the ongoing liquefaction processes. Another effect of liquefaction are sand boils. Here in this picture, we see a sand boil in Canterbury, New Zealand, this is related to the 2010-2011 Canterbury earthquake sequence that struck Christchurch in New Zealand, and this is a really super documented event in a super important case history in liquefaction studies. Other effect of liquefactions are settlements. This figure here shows settlements of the piers of the Juan Pablo II Bridge in Concepción. And this settlement was due to the 2010 Maule 8.8 earthquake that struck in Chile. We can see here that the piers 73 to 76, 113 to 116 settled, and amount was on average around half a meter, which is really important. And lastly, I want to talk about instability. A type of a very known instability is lateral spreading. In this, the failure of the soil due to grid shear stresses causes superficial layers to break, as we see here in this picture. And they move progressively towards a free phase. And for example, here is the coast, and this like layer of soils will tend to move towards the coast. And this picture shows a lateral spreading evidence in the port of Coronel, close to Concepción, and related to the same earthquake, the Maule earthquake 2010. The reason I expose this is because these effects have been observed in megathrust environments such as the Chilean subduction zones, and because they can lead to great damages in infrastructure and the harm of human lives. So, how do we want to tackle the problem of liquefaction in this research? A way to tackle the liquefaction problem is using numerical modeling, in which a site response analysis of a potentially liquefiable soil is performed. The requirements are, we need a constitutive model that can deal with the stress and strain relationship of the soil media. We need a prior knowledge of the soil characteristics in terms of data. We need the governing equation of motion and conservation for the soil media. We need an input time series for the earthquake loading of the soil base. And we need obviously a finite element or finite difference software for doing everything, all this mathematical, using this mathematical framework. The pros of numerical modeling are that it can model different phases of liquefaction. We can model pore pressure build up. We can model the triggering of liquefaction. We can model also the ongoing liquefaction during the earthquake and the post-liquefaction regime. A very important pro or advantage is that we can deal with 2D or 3D modeling, so that we can model lateral heterogeneities, which is very important for this research, because we want to model lateral heterogeneities and their influence in the soil response. It's a physics-based approach because it's also equations of motion and conservation, and there is less dependence on empirical relationships than other methods. Some constitutive models rely on empirical relationships, but it's less than other procedures that are not numerical modeling. And the cons can be that the post-triggering behavior is very challenging to model. For example, the process of modeling lateral spreading or post-liquefaction regime is something that deals with very large deformations, and this can be very challenging to grasp in numerical models. But this is something is kind of out of the scope of our research. We want to center mostly in pore pressure build up and triggering of liquefaction. Also, the constitutive model requires many parameters to be calibrated, and this is very important.
We lost your audio sometimes.
¿Cómo?
Se pierde tu sonido de repente.
It's okay for me.
For me too.
It's also okay for me. Yeah, okay, here fine.
Okay, so I will continue. Yeah, the cons I said about the I talk about the post-triggering behavior is very challenging to model, and the constitutive models require many parameters to be calibrated. Yes, this is really important to do, but it's also kind of out of the scope of this research itself, However, there are people from the same research group that are going to deal with this problem. But something we really want to tackle is the sparsity of in situ measurements. What I refer with the sparsity is that the data often is gotten from soil, from, for example, penetration test, the SPT or the CPT test that generate profiles of like a parameter type map. And we obviously cannot do a very dense map of this test because it's kind of expensive and invasive to do. But here we are going to present a methodology that we can get a 3D model with a lot of data by means of using by means of creating a shear wave velocity model. So what has been done in the past in previous research regarding soil variability and liquefaction? Here we'll talk a little about prior findings from Popescu et al. They found that stochastic fields can be employed for modeling soil variability. What is an stochastic field or modeling? In this case, the soil model parameters are generated from samples of multivariate probability density functions that are often non-Gaussian. And by using this kind of modeling, they found that spatial variability of soil properties influences liquefaction response. For example, if we have a soil and we use the mean value of the soil properties for like each layer, this will obviously neglect the presence of soil pockets within the soil mass, which can lead to underestimation of the liquefaction response. Let me elaborate a bit on this in the next slide. Here, in this image, we can see the excess pore pressure ratio depicted by this gray scale, in which a dark or gray color represents a high excess pore pressure ratio, and a white one represents little to no pore pressure ratio generation. On the upper part, we see stochastic models, and the lower part, we see deterministic models. Here we see sample functions generated, and we can observe that each of the sample functions have like have difference, but they seem to generate a pattern that generates a zone with high excess of pore pressure ratio. What we can see on the other hand in deterministic models, we can see that the average of soil properties, for example here using the average, leads to only a thin layer where the pore water pressure ratio is not negligible. And we will need to use, for example, the 70th percentile of the data in order to generate excess pore pressure ratio similar to what we see in the stochastic models. So this is what Popescu et al. Refers when using the layer models or like deterministic uniform models can lead to underrepresent the excess of pore pressure ratio and underrepresents the effects of the response of the site to liquefaction. In this table, I want to talk about a little about how soil variability in liquefaction has been assessed. For example, in Popescu et al., the variable data is the overburden stress, normalized cone tip resistance, and the soil classification index. They use, for numerical models, they use stochastic and uniform deterministic models. And in the constitutive model, they use the multi-jet plasticity model from Prevost. They do 2D and 3D models, and the input earthquake they generate is generated in such a way that the earthquake duration is 12 seconds, and the PGA varies from 0.08 to 0.35 Gs. Here we see something really interesting is that the duration of 12 seconds is is too low, is really low compared with the duration of megatrust earthquakes that it can last, like, for example, more than 1 minute. So this is a really important difference. The Montgomery and Boulanger 2015 research, the variable data is the overburden corrected blow counts, and the type of numerical model is are the stochastic and uniform deterministic models. They use the PM4SAM model, and they generate a 2D model. And the input earthquake in this case is a strike slip magnitude 7 earthquake at a distance of 10 kilometers. In the Brian Luke research, the variable data is also generated from cone and standard penetration tests, but they also use the small strain stiffness of soil layers computed from CPT and from multi-channel analysis for surface waves. They use the deterministic models. They do 2D analysis and use the PM4SAM model. And the input earthquake is from the Canterbury earthquake sequence, and it varies from magnitude 5 to magnitude 7 strike slip earthquakes at depth around 10 kilometers. The remarks are that the CPT and SPT data is the most used for modeling the variability, but a study uses gets VS through MassW, so there is documentation of using VS for modeling spatial variability. Another important thing is that the studies don't generate input earthquakes from megatrust environments. And a question we can ask ourselves is that, do we need stochastic models when data coverage is dense? And with that I mean, if we have a lot of data, perhaps the benefits of generating a stochastic random model will not be necessary. So how we are going to model soil variability? What we want to use is the shear wave velocity, or VS. VS is defined mathematically as the square of the ratio of the shear modulus to the density. We know that D0 and ρ are input parameters for soil constituted models, and therefore they will affect the model response and performance. But most importantly, and what we want to or interest in this research is that VS is inherently linked to the soil structure and how waves propagate through media. So a great lateral or vertical disturbance in soil structure will affect the wave path, and ultimately this might influence the site response to liquefaction. And this last affirmation is what we want to prove in this research. We can get a VS model by means of a seismic wave tomography. And in a seismic wave tomography, it uses seismic waves arriving to recorders A and B and this can be from known or unknown sources ubication to generate wave velocity models. Seismic wave velocity tomography is a physics-based, thoroughly cited, non-invasive, and non-expensive method for exploring the subsurface. And these applications range from cross-upper mantle velocity models to engineering seismology applications. And the depth of or shallowness we can reach depends on the wavelength of the received wave at the receivers. So here we see a 3D S velocity model from the Pilz et al. 2012 research. This site study is ubicated in Northeast Germany, and here we see like layers, 2D layers of the 3D soil model they generated. These black dots represent the place of the receivers, and the black lines represent the right coverage in between the sensors in the model. This was created from an ambient noise surface wave tomography, which uses the noise of the microtremor wave field to create the S velocity model. and we can appreciate that there is an increase in the wave velocity from 5 meters to 5 to 10, 10 to 15, and 15 to 20. There is an increase in velocity with depth, but we can also see there is, for example, here in this layer, lateral variability or heterogeneities in a same layer, and something like this is what we want to get in our model. We want to see if the is a site is lateral, there is important lateral variabilities, and input this in our constitutive model in order to generate a site response and see if this is important for liquefaction assessment. So in order to do that, we need a case study. Our case study is the Condominio Los Presidentes. This is a 4-story building. This was a 4-story building at the time of the earthquake, this is the Maule earthquake, but nowadays has 6 buildings. This condominium was subject to liquefaction-induced damage and surface manifestation of liquefaction because of the Maule earthquake. And there was variability in surface manifestation of liquefaction, and 2 buildings exhibit settlements and needed to be demolished and rebuilt. For example, here in this picture, we see a LiDAR image from Cayenne, from a Cayenne workshop, and we see the building settlements of each of the buildings. For example, we see that the Errázuriz and Riesco buildings, which needed to be rebuilt, exhibit an important amount of settlement. For example, here the Riesco in the northeastern corner exhibit a settlement of 34.5 centimeters, and in the northwestern corner it exhibit a settlement of 6.9 centimeters. So an important differential settlement was occurred in the site. But most importantly, and I think it's really interesting, is that the building, which is only a few meters away, exhibit 0 settlements. And this is, and yeah, there could be a bunch of reasons of why this happened, but we can also think that maybe a different soil response to liquefaction related to soil variability could be an important reason. So that leads us to the hypothesis. Our hypothesis is that the 3D variability of DS influences the site response to liquefaction, since it's inherently related to how waves propagate through media. And our second hypothesis is that a 3D DS model can be used as a proxy for assessing the influence of soil variability in the occurrence of earthquake-induced liquefaction in subduction zones. Which is our main goal? Our main goal is to assess the influence of 3D soil variability proxied by the shear wave velocity in the occurrence of liquefaction in the condominium Los Presidentes due to the Maule 2010 magnitude 8.8 earthquake. And the specific goals are to obtain the 3D shear wave velocity model of the site by means of an ambient noise surface wave tomography, to create a 3D soil model of the site from the tomographic inversion, and perform an effective stress analysis applying a cyclic loading representative of the Maule 2010 earthquake, and to compare the performance of different constitutive models. Okay, I am going to talk now about the methodology. First, I will talk about exploring the surface with ambient noise. Man-made sources in the microtremor band carry frequency content which can be exploited to map the very first meter of the soil. In particular, the spatial autocorrelation or SPAC method, owed to Aki, is employed in this thesis. This method states that the temporal average of the correlation function in the frequency domain between two stations is related to the phase velocity by this equation, as long as there is not great directivity in the noise. Here, G0 is the zero Bessel function of the first kind. Omega 0 is the angular frequency. C as a function of omega 0 is the phase velocity, and R is the intersection distance. The noise correlation function between station X and Y can be obtained with the cross coherence of M segments for the two recorders. So here we have the noise correlation function. It will be equal to the real part of the auto spectrum of X and Y recorders divided on M segments and normalized by the auto spectral density of the X recorder and the Y recorder, which are the equations 1 and 2. How we can retrieve dispersion curves? We can obtain the dispersion curve C by matching equations 1 and 2. We decided to use the Menke and Jean 2015 waveform fitting method for obtaining a reliable dispersion curve. Why we use this method? Because it works. It has shown good results when the signal to noise ratio is not high enough, which is a problem we may encounter in our case study. Firstly, we need to obtain a coarse estimate of the phase velocity by minimizing the L2 error with the grid search, and that means to minimize this equation. If we let M be equal to C, be the model parameter, we will be in presence of an inverse problem, which is nonlinear. Why is nonlinear? Because we will relate the kernel as a function of M. M will be inside of this Bessel function. Obviously, this is a nonlinear. There is no way to take out M of the equation, and that's the reason the inverse problem is nonlinear. However, we can linearize the inverse problem and express it as a product of like a kernel matrix and the model parameter around our grid search solution from this part, and use this estimate with the Newton iterative method to find a global minimum of the error. We need to be careful because if our grid search solution is not close enough to like a plausible solution, the solution found will be not a global minimum. It will be a local minimum, and there will be no physical validation of the result. And also we impose Laplacian smoothing in the phase velocity values so that no big jumps in phase velocities occur. How we are going to process the data? Yeah, so we do a microtremor noise surveys, and the recorded time is around 40 minutes. We know this is not the ideal recording time, but the literature says that, and my experience with the preliminary result, it shows that it should be enough. Then we detrend, demean, taper, and divide into segment the data from the receivers. We apply a high pass filter and 1-bit normalization if needed. We then compute the cross coherence and stack the causal and acausal parts of the cross correlation. And then we retrieve the dispersion curves with the Menke and Jean 2015 methodology. So now we have the dispersion curves. We can proceed to generate the shear wave velocity model. The linearized travel time equation says that the time is a linear combination of the slowness and is given by this equation, where L1 is an RF times Mn matrix, with R being the number of rays for F different frequencies crossing a medium subdivided into M cells in each of the N horizontal layers. Phase velocity is assumed to be constant within each cell. What I mean with that is like simply scheme in this shear figure, in this figure from the shear book. For example, if we in this case we have 8 cells, that will be M equals to 8. In each of the N horizontal layers, we have 1, 2, 3, 4 layers. And for example, if we assume this is a right path, if we assume that if we assume here that more than one right path crosses for each one of the blocks, we will have here the R, the number of rays. And lastly, if we assume that this ray is not monochromatic and is composed by more than one frequency, we will have different frequencies for each ray. An iterative approach is used for solving this equation 5, and we impose weights in L1 and constraint in the solution to stabilize it. And the S-wave velocity ds will be can be obtained from this equation, where S is slowness and C is the phase velocity. So now I want to talk a little about the soil constitutive modeling. So when a soil element is subject to stresses, elastic and plastic strain take place simultaneously. The assumptions we're going to make are the same that were made in the Chan and Parra-Colmenares PhD thesis. First assumption is that elastic strain can be decomposed in an elastic and an aplastic part. And we also assume that elastic strain is linear and isotropic, and the plastic strain is non-linear and anisotropic. The elastic strain is described by the Hooke's law, and the plastic strain will be described by different soil constitutive models, and a constitutive equation relating elastoplastic stress-strain behavior can be written as this. Here, the dot over the stress and strain represent that this is an incremental description. That is, we are going to deal with changes in strain and changes in strain. E is this is the elastic coefficient tensor. P is the tensor defining the direction of the formation in the stress space, and L is the plastic loading function. We also use the effective stress equation that relates the effective stress and is equal to the sum of the normal stresses, or the total stresses, I mean, and the pore pressure. And we use the UP formulation in which the displacement of the solid phase U and the pore fluid pressure P are the main variables. And this equation here combines different equations that describe the fluid-solid motion, the fluid-solid mass conservation, and the Darcy's law of flow through porous medium. This, along with proper boundary and initial conditions, yield a strong formulation, which can be worked onto a weak formulation for a finite element implementation. So, in resume, yeah, I think you cannot see here in my screen because this is hidden by my screen. But here we do the microtremor noise surveys. Then we process the data according to Benson et al. And Chu et al. We retrieve the dispersion curves with the Mencken-Jean methodology, and we compute the 3D shear wave velocity model with the Pitts et al. 2012 methodology. We also get the average light properties as well. And then with this, we perform an effective stress analysis in the OpenSys finite element software. This is an open source software that's really using in geotechnical engineering applications. With this, we can assess the influence of the constitutive models, and we can also test different constitutive models, such as the three we have here. We can assess the influence of variability of DS variability by doing a 3D variable model and an layered model, and we can also analyze the performance of DS as a proxy. And also we can constrain our modeling with available geotechnical and geoelectrical data getting retrieved in the research project. Here we have a work schedule that I think I will skip because of the time. And I'm going to talk about our preliminary results and the conducted surveys. Here, the first survey we conducted was a kind of regular surveys. Here, the blue dots represent the first part of the survey, and the red dots represent the second part. So here we you use a minimum interstation distance of around 10 meters. But a suggestion from the committee was that, well, firstly, that the minimum interpretation distance was to hike to retrieve to get data in the high frequency noise, and also having a constant interstation distance will be kind of redundant in the if we want to will be kind of redundant, and having like more variable interstation distance will us to image the subsurface in a more precise way or dense way. So because of that, we conducted another survey. Here's the part 1 of the survey, and this is the part 2. And the minimum insertion distance in this case was around 4 meters. So this is the dispersion curve inversion of we have done. First, here I show a synthetic cross coherence fit example. We did generate a target model depicted here in a target phase velocity model depicted here in by the green pointed line, and the estimated phase velocity we got with the Menke and Jin methodology is this one. We can see this curve we retrieved is kind of smooth, but it's really similar to the true phase velocity. The target correlation function or the target data here is the black line, and this one was generated from the phase velocity model, but we also imposed a correlated Gaussian noise in order to perturbate the data. And this we see that there is a good agreement in the feed of the feed of the data and the target data. Then we also did with the real cross coherence data with the surface we did at the condominium. Here I show in the black line is the grid search phase velocity, and this is like our initial solution, and the red line is the Newton phase velocity solution. We can see that there is like obviously the grid search solution is kind of like is composed by linear it's composed by linear functions, and it's kind of like really like not smooth. And the Newton phase velocity and the phase velocity obtained from the Newton method is kind of like more smooth, and also it fits the data better, as we see here in this plot. Here we see the target correlation function, and we can see that this is kind of like a bit of noisy. The green line is the estimated correlation function from the grid search. This is our first step. We see that the fit is not that good, and then and we can also see the estimated correlation function from using the Newton method, which is kind of like more similar to the target correlation function. So yeah. Here we can see the bibliography. This was like my presentation, and thank you very much.
Okay, thank you very much, Sebastian. I will stop the recording now.